All right, so today we are in chapter 0, lesson 4, talking about simplifying expressions in radical form first, and then we'll get to exponential form next. They are closely related, which we'll talk about. But first, let's talk about radicals and specifically nth roots. Remember that if a equals b to the power of n, then that means that the nth root of a would be equal to b. For example, since 16 is equal to 2 to the power of 4, that means that the fourth root of 16 is 2. You can multiply 2 by itself 4 times and get 16. Basically, an nth root is asking you what number can you raise to the power of n to get the value of the radicand, or the number under the root. So like this is saying, what number can you raise to the power of 4 to get 16? It's 2. Remember that if there's no spot written on the root, that's just a square root. It's a 2. It's just implied. Okay, let's try some examples together. So this one says evaluate each of the following expressions. We are looking at -2 square root of 49. I know that's a square root because there's no number on it. So I'm thinking, what can multiply by itself twice to get 49? Everyone should know that's a 7. So this is equal to -2 times 7, which is -14. On the next one, I'm looking at the cube root of 64 over 27. You can split this up. You can split up the cube root of the numerator and the cube root of the denominator. These are both perfect cubes. I can multiply 4 times 4 times 4 to get 64. Since 4 cubed is equal to 64, that cube and cube root cancel each other out. So that's just a 4 on top. And I know that 3 cubed is equal to 27, so I can substitute in 3 cubed for 27. The cubed root of 27 is just 3 on the bottom. So that leaves me with 4/3 as my final answer for B. And finally, for C, I have the fourth root of -121. That one, it's an even root of a negative number. I can't multiply a number by itself 4 times and get a negative number. So that one has no real answer. Now, if it was a square root, I could use I, the imaginary number, but it's a fourth root, so I'm just going to write no real answer. Try the practice problems, and I'll show you the answers to those. Here are the problems for A and B. And then here is C, similar to the last one. It's an even root of a negative number, so that's not a real number. Answer. And next we'll talk about some properties of radicals. This is not going to be tested, but it might come up in your homework or just in general if you see it. I don't want you to be confused why they're throwing absolute values in there. Here's the thing. If you find an even root of an even power and the result is an odd power, you have to use absolute value of the result to ensure that the answer is non-negative. So I would just suggest remembering even root of an even power and the answer is odd. That's when you use an absolute value. Let's do some practice with that together. So if I have the sixth root of n to the 18, it's saying what can I multiply by itself 6 times to get n to the 18? If you have a variable raised to a power, you can make a factor tree for this, n to the 18, and you would find out that if you multiply n cubed by itself 6 times, let's see, I need 6 of these. I need one more. You would get 18 because you know that you add the exponents when you multiply. So that would give us 18. But really, the shortcut is take the power, 18, divide it by the number on the radical. 18 divided by 6 is 3. So rather than sitting here and trying to figure out the factor tree, I would just get rid of that. What we're going to do is we're going to take 18, divide it by the number on the radical 6, it's 3. So you have the option to write this as n cubed to the power of 6, because we know a power to a power you multiply. So n cubed to the power of 6 is the same as n to the 18th. And then canceling out the 6th root with the 6th power to give us n cubed. Or if you want to go straight to that answer n cubed, that's fine too. You're dividing the power by the number on the radical. Notice, we did the even root of an even power, and the answer was odd. We have to put an absolute value around this. The next one, it has two parts here. We have the factor 81, and then we have the factor a plus 1 to the power of 12. Let's treat those separately. First, the 4th root of 81. 81 is equal to 9 times 9, which are both perfect squares, 3 times 3. So since I have 4 factors of 3, I know that could be written as 3 to the 4th instead of 81. And I can cancel out the 4th root and the 4th power. The 4th root of 81 is 3. You can separate this out. Now do the other factor. The 4th root of a plus 1 to the power of 12. Just like the last problem, take the power of 12, divide it by the number on the radical, 4. 12 divided by 4 is exactly 3. Remainder is 0. That means I can pull this out of the radical, put a plus 1 to the power of 3, because 12 divided by 4 is 3. If you wanted, you could put to the power of 3, then the power of 4, and cancel it out. Either way, your answer is 3 times a plus 1 to the power of 3. Double check. Did we have any even roots of even powers? Yes. We did the even root of an even power, and the answer was odd. Since the answer is odd, we have to put an absolute value around that. Next, problem C. The square root of 63, y cubed. 63. Let's look at a factor tree for that. Does it have any perfect squares in it? I know that a 3 can go into that because 6 plus 3 is 9, and 9 is divisible by 3. Therefore, 63 is divisible by 3. It's 21, and that is equal to 3 times 7. I do have a perfect square here, 3 times 3. So I know that could be written as 3 squared and 7. The 3 can come out of the radical because it's a perfect square, but the 7 has to stay under the radical. It's not a perfect square. It doesn't have a factor that's a perfect square. Similarly on y cubed, the square root of y cubed. When I think about taking that power of 3 and dividing it by the number on the radical 2, it doesn't go in evenly. It's 1 with a remainder of 1. So you can think of this on a factor tree. If you had y cubed, it's y squared times y. The square root of y squared is going to give me y. But the square root of y cannot be simplified. It's kind of like how the 7, it wasn't a perfect square, so it had to stay under the root. The y is not a perfect square, so it has to stay under the root. Notice that 1 factor of y came out, and 1 factor of y remained under the root. Whatever the whole number part is, that's what gets to come out. That's the power of y's that get to come out of the root. Whatever the remainder is, that's the power of y's that have to stay under the root. Now let's put these two answers together. On the outside of the root, we have 3y. Under the root, we have 7y. That's your final answer. Oh, double check. Do we do even roots of even powers? No, so we're good. We don't have to worry about a square root. All right. Now we have the fifth root of negative p to the 10th, q to the 7th. All right, for the next one, you have to pay attention that this coefficient is a -1. So first we have the fifth root of -1. This is an odd root of a negative, so that's fine. -1 times -1 times -1 times -1 times -1 5 times is going to be equal to -1. So the fifth root of -1 is simply -1. The fifth root of p to the 10th, we're going to take the power of 10 divided by 5. That gives us 2, exactly 2 with no remainder. So I know that's p squared. And then the fifth root of q to the 7th, when I divide 7 by 5, I get 1 with a remainder of 2. So I know that one factor of q can come out, and I am left with 2 factors of q under the root. Similar to the last problem, the whole number part tells you the number of factors that can come out. The remainder tells you the number of factors that have to stay under the root. And one thing to correct here is that this is still a fifth root, not a square root. So make sure you keep that fifth root on there. Now let's put this all together. We have -1 p squared q on the outside of the root. So we'll just put negative p squared q. And then under the fifth root, we have q squared. That would be your final answer for problem D. Go ahead and try the practice problems that are on the right, and I'll show you the correct answers. Here are the answers for those. Notice you have absolute values on A and B. That's because you took the even root of an even exponent and you got an odd answer. And that wraps us up for radicals. Now we're going to look at exponent form. Keep in mind, rational exponents are just the same as a radical. So exponents and radicals are really closely related. The top number tells you the exponent on the base. The bottom number tells you what's the root on the outside. Now it doesn't really matter if you want to put the power in under the radical or outside the radical. It's the same thing. Let's try some of these together. We want to simplify this 10th root of 32 over the 6th root of 2. When you see this, you'll notice they have different roots. They have different bases. It's going to be helpful to get these to be the same base. I don't know what the 10th root of 32 is. I don't know off the top of my head what can I multiply by itself 10 times to get 32. It's not a perfect root. Same with the denominator. I have no clue what can multiply by itself 6 times to get 2. So what's going to be helpful is to make these the same base. If I rewrite this in a base of 2, 32, I can make this a base of 2. Because 32 is 2 times 16. 16 is 2 times 8. And 8, I know, is 2 cubed. So 32 is the same as 2 to the power of 5. Now these both have a base of 2. Let's write them in exponent form. This would be 5/10. This would be 1/6. Remember, the top number tells you the power, the bottom number tells you the root. Keep in mind, when you have division and they have the same base, you can subtract the exponents to simplify this. So I can go 5/10 minus 1/6 on the base of 2. This only works if the bases are the same. That's why I wanted to get the bases the same to begin with. Now for subtracting or adding fractions, I need common denominators. I'm going to go ahead and simplify this, make this 2 to the power of 1/2 minus 1/6. My common denominator, or the least common multiple of 2 and 6, is 6. My second fraction already has a denominator of 6, but my first does not. I can multiply by 3/3. which is a sneaky form of 1, to make these have common denominators. 3/6 is the same value as 1/2. So I haven't changed this problem. I've just changed what it looks like. But now I can actually subtract 3 minus 1 to get 2 and keep the denominator 6. These both share a common factor of 2, so I'm going to divide out the common factor of 2 on the top and bottom to get 1/3. So I know this is equal to 2 to the power of 1/3. That's one way to write the answer, or you can write this as the cube root of 2. Either way is great. There's a practice problem with the answer for you. And you might want to fill in the little box here about simplifying exponents, about subtracting the exponents to simplify, so that you don't forget that. And then we'll go to the next page for another practice problem. So we have the x to the 21st, y to the 15th, raised to the power of 1/4. You have a couple options here. You can, since this is just one term, you can distribute this power. Remember, you can do that when it's one term in the parentheses, but not when it's two terms. Or you can put this all into radical form. I think I would prefer that. So we have the 4th root of x to the 21, y to the 15th. Now this turns into a problem that we already did in the last problem set where we were working on radicals. We're going to take 21 divided by 4. It's 5 with a remainder of 1. 15 divided by 4 is 3 with a remainder of 3. Yep. And then I know that 5 factors of x get to come out of the root. And 1 factor, oops, didn't switch to my highlighter there. 1 factor of x needs to stay under the root. Similarly, 3 factors of y get to come out. 3 factors of y have to stay under. Now putting these two together, I have x to the 5th, y cubed on the outside of the root. Under the root, I have xy cubed. All right. Now on the next problem, I'm looking at 27 to the 1/2 power times 27 to the 1/3 power, all over 3 to the 1/4 power. I notice that these on top have the same base, so in order to multiply them, I have to add their exponents. So I need to add 1/2 plus 1/3 first. I would need a common denominator, which is going to be 6, the least common multiple. And that's going to be 3/6 plus 2/6, which makes 5/6. So on the top, I have 3 to the power of 5/6. I'm sorry, 27 is my base there, to the power of 5/6. On the denominator, I have 3 to the power of 1/4. Now, in order to do anything with those two, I would have to have the same base, but I know 27 can be written as a base of 3. So I know 27 off the top of my head is 3 cubed. So I'm going to replace the 27 with 3 cubed, keep the power of 5/6 on the outside. A power to a power, I can multiply to simplify that. So I can do 3/1 times 5/6. Can divide these both by their common factor of 3 before I multiply. I get 5/2. Now I have the same base, so I can subtract 5/2 minus 1/4. My common denominator is going to be a 4. My second fraction already has that denominator. My first needs to multiply by 2/2. So 10/4 is equivalent to 5/2. So I'm still working on this same problem. but I get 10 minus 1 is 9, and my denominator is 4. So you can write your answer like that, 3 to the power of 9/4, or you can write the 4th root of 3 to the power of 9. Looking at it in root form, I can tell that that can simplify because the power under the root is larger than the radical. So I'm going to take 9 divided by 4. It is 2, remainder 1. So I know 2 powers of 3, or 2 factors of 3 get to come out of the root. 1 factor of 3 has to stay under the root. Sorry, I'm really squeezing this in here. 3 squared simplifies to 9. So I have a 9 on the outside, and then the 4th root of 3. That was a really hard problem. So it gave me 9 times the 4th root of 3. The practice problem for this one is a lot easier because they already have the same base, and they already have the same denominator on the exponent, so that'll be a lot easier for you guys when you try to do that by yourself. Here are those 2 practice problems, C and B, the final answers for them. I'll kind of block this so you can see that's not with that problem. And then once you get those 2 done, that's it for simplifying radicals and exponents. You really have to be a pro at your rules of exponents, so if you're not quite up to date on those, go back and review them. You need to remember when to subtract the exponents, when to add the exponents, when to multiply the exponents. So go back and practice those if you need to. See you guys again next for solving systems of equations.